Assalamualaikum and hi. Before we get started, let's meet our group members. First, my name is Siti Nur Adia and my matrix number is 2023605148.
Assalamualaikum and hi. My name is Nurin Amalina binti Rahimi and my matrix number is 2023684336.
Assalamualaikum and hi. My name is Nohina Shaira. My matrix number is 2023844012.
Assalamualaikum and hi. My name is Hashimah binti Abdul Ghani. My matric number is 2023858022. In this video, we are going to explain about Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, frictional force, and also free body diagram. So let's get started. Newton's law is a branch of mechanics. Mechanics is the study of motion of objects and the related concept of force and energy. Force is an agent that produces or tends to produce acceleration or causes a free body to undergo a change in speed, a change in direction, or a change in shape. Force cannot be seen, but we are able to see and feel the effects of force if it acted on things. The SI unit for force is in Newton. According to Newton's first law, an object will continue to remain at rest or in uniform motion unless acted upon by an external unbalanced force. But in real life, we often see things like balls eventually stop. Why? It's because of frictions. Without frictions or air resistance, the object will just keep moving forever. This idea is called inertia. Inertia is just how much something resists changes. Heavier objects have more inertia. For example, it's much harder to push a couch than a small chair. And if all the forces acting on an object are balanced, we call that equilibrium. That's when net force is equal to 0. If you push a box with 5 Newton to the right and your friend push 5 Newton to the left, it doesn't move. Why? Because the total forces is 0. That's called equilibrium. Here's another example. When you are in the car and it stops suddenly, have you felt yourself lean forward? That inertia. Your body wants to keep moving even though the car has stopped. That's why we wear seatbelts. They act as the external force that stops us from flying forward. Now let's apply all this to real example. Little Miss Sunshine is standing still on a ramp elevated at 15 degrees to the horizontal. If she has a mass of 15 kilograms, calculate all the forces. The moment we see the term like standing still, at rest, uniform velocity, we know we are dealing with Newton's first law with accelerations of 0. First thing first, we draw the free body diagram. In this FBD, we have 3 main forces. First one is weight or Fg, which pulls straight down due to gravity. Second one is normal forces, Fn, that push out perpendicular to the ramp. Next one is the static friction force, FFS, acts up to ramp, stopping her from sliding. To simplify the problems, we split the weight into 2 components. The first one is along the ramp or x-axis, we call as FGX. The next one is perpendicular to the ramp, y-axis, FGY. Next, we calculate the gravity force using the formula of Fg equal to m multiplied by g. And then we get 50 kilograms multiplied by 9.81 ms squared. And the total becomes 490.5 newtons. Next, let's focus on the x directions, which means parallel to the ramp. So, from the FBD, sum of Fx is equal to force of friction plus Fgx. To complete the calculations, we first need to find the value of Fgx. Since gravity acts vertically and the ramp is 15 degrees, Fgx is on the opposite side of triangle. So we use sine. Now we got Fgx equal to negative mg sine 15 degrees. The negative sign shows it pulls down the ramp, which is the negative x directions. Now, since Miss Sunshine is standing still, we know that the acceleration is equal to 0. That tells us that sum of net forces for x-axis is equal to 0. Then I will say the 0 equal to Ffs plus Fgx. Then move friction force to the left side and substitute the value of Fgx in the formula. Then we got the total of 127 newtons. Now let's look at y directions, which is perpendicular to the ramp. Here we have Mgy, which is the component of gravity pushing into the ramp, and we have Fn, the ramp pushing back upward. To complete the calculations, we first need to find the value of Mgy. Since this is the adjacent sides, we use cosines. Now we got Fgy equal to negative Fg cos 15 degrees. Again, this function is not accelerating, so sum of net forces for y-axis also equal to 0. Then I will say 0 equal to Fn plus Fgy. Then I will move normal forces to the left side and substitute the value of Fgy in the formula. Then we got the total of 143 Newton. All forces are balanced on both directions. That's why she stays perfectly still.
Newton's second law of motion. Newton's second law of motion can be started as the rate of change of momentum of a body is directly proportional to the resultant force on it and is in the same direction as the resultant force. Newton's second law is represented by the expression
Using Newton's second law of motion, which states that force equals mass multiplied by acceleration, we can understand how different carts require different amounts of force to move. Let's go for the question. We have empty cart and full cart. Solution: in the first scenario, empty cart has a mass of 10 kg and is accelerated at 2 m/s². By applying the formula F equals 10 multiplied 2, we find that only 20 newtons of force is needed to push the empty cart. In contrast, the second scenario involves a full cart with a mass of 30 kg but the same acceleration of 2 m/s². Using the formula again, F equals 30 multiplied by 2, we got 16 newtons. This means that to push the full cart at the same speed, you need 3 times more force than for the empty one. This clearly demonstrates Newton's second law in real life. Greater the force need to accelerate it at the same rate.
Newton's third law of motion. Every action has a reaction, which is of the same magnitude or opposite in direction. Anytime a force exerted on an object, the force is caused by another object. In other words, Newton's third law involved two different bodies.
According to Newton's third law of motion, for every action, there is an equal and opposite reaction. In this case, when the swimmer pushes the wall of the pool with a force of 150 Newton, the wall pushes back on the swimmer with an equal force of 150 Newtons. However, this reaction force acts in the opposite direction to the one the swimmer applied. So, if the swimmer pushes backward against the wall pushes them forward with the same amount of force. This reaction force is what propels the swimmer forward through the water. This example perfectly illustrates Newton's third law of force. Always come in pairs that are equal in size but opposite in direction.
Frictional force. Frictional force is the force that opposes the relative motion of two surfaces in contact. The direction of force is always parallel to the surface in contact and is always perpendicular to the direction force. Free body diagrams. free body diagram is a force diagram showing all elements in the diagram, axes, vectors, components, and angles.
You will fail physics if you don't understand free body diagrams. If you can't break down forces, you can't solve anything. Let's fix that right now. This is an object. Could be a box, a car, or anything you can think of. Everything has forces acting on it. First force is gravity, and it always pulls down. M is mass, G is 9.8, and this force will always be here. If it's sitting on something, we also have a normal force pushing up called Fn. This keeps objects from falling through surfaces. Without this, you'd sink into the floor like quicksand. Now, if we push this thing, that's an applied force. Could be from a person, an engine, or even the wind. If something moves, there's a force making it happen. And friction is what's fighting back. It resists motion. More friction, harder to move. Less friction, ice skating. Without friction, you'd never stop sliding. But forces aren't always straight. If something is on a ramp, then gravity splits into two parts. One pulling it down, one pushing into the surface. The steeper the ramp, the faster it slides. This is your free body diagram. Every physics problem with forces starts...
Next, I want to share another example about a real-life application of Newton's law using a free body diagram and frictional force. Imagine a 10 kg box is being pushed horizontally on a rough surface with a force of 15 Newton. The coefficient of kinetic friction between the box and the floor is 0.3. What is the acceleration of the box? First, let us begin with draw the free body diagram. The box experiences four forces. It experiences gravity pull it down, the floor push up with a normal force, a pushing force move it to the right, and friction act to the left. Alright, now let's go through the step-by-step calculation together. First, share what we know from the question. The mass of the box is 10 kilograms. A horizontal force of 50 newtons is being applied to push it. The surface is a bit rough with a coefficient of kinetic friction of 0.3. And as always, we will use gravity as 9.81 meters per second squared. Now, for step 1, we calculate the normal force. Since the box is on a flat horizontal surface and there is no vertical movement, the normal force is equal to the weight of the box. So, we multiply mass by gravity. 10 times 9.81 gives us 98.1 newtons. Moving to the step 2, we calculate the friction force. Friction is found by multiplying the coefficient of friction by the normal force. That's 0.3 times 98.1, which equal to 29.43 newtons. Step 3, we determine the net force acting on the box. To do that, we subtract the frictional force from the applied force. So, 50 Newton minus 29.43 gives us a net force of 20.57 newtons. And finally, step 4, we use Newton's second law to find the acceleration. Acceleration is force divided by mass. So, we take 20.57 divided by 10 and we will get 2.057 meters per second squared. So, the box accelerates forward at exactly 2.057 meters per second squared.
In summary, this presentation has highlighted the essential principles of mechanics that govern motion and force. We have discussed Newton's first, second, and third law of motion, emphasizing how each law explains the behavior of objects under various conditions. The rules of frictional force was explored in relation to motion resistance and surface interactions, while free body diagram would use to illustrate the force acting upon objects in a clear and structured manner. Together, this concept forms the foundation for analyzing mechanical systems and understanding how different forces interact. By applying these principles, one can predict and explain the outcome of various physical situations. We hope this presentation has provided a clear and cohesive overview of the key mechanics concept and and their interrelationship.